So we're talking about power, and power is just how fast you can do work. I was thinking about this on my way to school. The place that you are probably most familiar with power ratings is on little motors. Little blower motors on furnaces have horsepower ratings. Horsepower is the old imperial unit for power. We're a little bit more sophisticated than that now. We use watts. But power is the rate at which work is done. So it's work over time. And we can derive, because we know that work is FD, power is F times D over T, which means that power is force times velocity. Gets us the same thing. Sometimes this is helpful. We'll see where. What units? Get it? Watt, units, watts. Okay. You'll think it's funny later. You can use it on your friends and family. The unit we use now is the watt, which is a joule per second. Now, a joule is not a whole lot of energy. If you think about, thanks, you're smiling. See, you can't resist. You know it's funny, and you know you'll tell it to somebody later. If we go and break this down backwards, we don't usually use watts because they're such a tiny little unit of energy. So let's actually do some backwards dimensional analysis. What's 1 Newton? 1 kilogram accelerated at 1 meter per second squared. So we have kilogram masses there. You've handled them. You know what a kilogram feels like. It's not a whole lot of mass. So it takes 1 Newton of force to accelerate that at 1 meter per second squared. Well, we said that 1 joule is equal to 1 kilogram meter per second squared pushed for a meter. So taking that 1 kilogram mass and accelerating it at 1 meter per second squared over the distance of 1 meter. And you know what 1 meter looks like. You've handled meter sticks. Well, we're saying that 1 watt is 1 kilogram, we're up to meter squared now, per second squared per second. So we're doing the amount of work needed to take that 1 kilogram mass, accelerate it at 1 meter per second squared for 1 meter, and we're doing that in a second. It's not really a whole lot of output. That's pretty small change. Because a joule is not a whole lot of power, I'm sorry, a watt is not a whole lot of power. So we usually use kilowatts, which are how many watts? 1,000 watts. And we can get into electric bills and everything else, but we won't for right now. If we've got 2 motors, has anybody here ever butchered chickens? Butchered chickens. And then
kill one?
And then pluck the feathers and then cook it. Okay. So after the chicken is deceased, before you eat it, you got to remove the feathers. You knew this part, right? You've all eaten chicken. Has anybody here? Have you eaten chicken? Okay, good. You've seen live chickens, or at least pictures of them. You've eaten dead chickens. As my daughter likes to say, we don't eat the live ones. That's right. In between the live chicken and the chicken on your plate, it's got to get plucked. And so one of the most common plucking mechanisms, I'm going to draw this for all you backyard Appalachian engineers. Appalachian engineers, you should understand, is completely a term of endearment. This is the whole sort of like farm kid can do, well, let's see, what do I have in the barn? Yeah, I can build something that'll do that. That's Appalachian engineering, and it is a wonderful thing. So, a chicken plucker. This is a tub. I have seen them made out of old laundry tubs. Remember the little laundry tubs have all these little holes in the side? And they sell what are called plucker fingers. It is a rubber finger that sticks into the tub. So looking down into the tub, you would see it's like a hairbrush turned inside out. And these are made of rubber. which means they have a relatively high coefficient of friction. And coming up through the center of the tub is a little drive. And attached to the bottom of that drive, there's usually something that changes the direction of the force. But the most common way to make these, and the way I looked at them, is you can get old furnace blower mowers really cheap. Somebody tears out their furnace, but the blower mower is fine. You know, 10 to 30 bucks will get you a little furnace blower motor. And you power up this tub, you throw the dead chicken in here, you turn the sucker on. This is really cool. And those rubber fingers grab the feathers, and it plucks the chicken for you. Now, nobody here has ever plucked a chicken by hand? Let me tell you, this is a vast improvement. This is a quality of life improvement right here, because I've plucked a lot of stuff, and this will change your life. And yet, I never did build one. I looked at plans a lot. You want to get the right amount of power in that motor. So I've butchered more turkeys than chickens, oddly enough. And the same motor that will pluck a chicken easily, chicken's like 4 to 6 pounds. Turkey weighs significantly more than that, more mass. So this is like putting, they don't even do the merry-go-round pushy things on the playground anymore. They're too dangerous. It's ridiculous. People need to get your heads split open once or twice just for good measure. That's an experience. So if you have a whole lot of mass with a small amount of power turning it, that motor does not have sufficient power to do the work. That's really what we're looking at here. We're looking at work and power. And you can see, a 375 watt motor is about a half a horse. The ones that you find pretty commonly are like 1/3 horsepower motors, which is 250, 275. Not enough to pluck a turkey. I'll just tell you that. And you can look up chicken and turkey plucker motor designs on YouTube. There's a whole community of people building chicken pluckers in their backyards. I love them. So let's actually look at those two motors and do a quick calc. Okay, so 500 joules of work is needed. We have the option for two motors, one with a 750 watt rating, one with a 375 watt rating. How long will each take to complete the task? Well, the fact is, delta T is equal to work divided by power. Remember your units. Your time is going to be in what units, based on all the dimensional analysis that we did? Seconds. So we're talking about seconds here. For the first motor, delta T equals 500 joules divided by 750 watts. How long will that motor, the 1 horsepower motor, or the 750 joule motor, take to accomplish the task? Okay, so for the first motor, it'll be under a second, 0.7 seconds, 0.6 repeating. What about the second motor? Okay, that's what I get for doing problems off the top of my head. With one sig thing, it would be a second. It'll be a little over a second. Looking at our raw values, we know that this will take a little over a second to complete the same task. It's not a whole lot of difference, but 500 joules is also not a whole lot of work. So let's do a sample problem. This problem might be near and dear to your heart if you've done stage crew, which I think a few of you have had some involvement there. We have a curtain that needs to be raised 7.5 meters. Now that's a very tall stage opening. At constant speed in as close to 5 seconds as possible. They want a 5-second curtain rise. If you've ever seen, who here has seen the Nutcracker on stage? You should go. You should someday go see it. It's beautiful. The big key scene is the Christmas tree growing. So, we go into Clara's dream world, and the Christmas tree, the back curtain rises and pulls the Christmas tree with it, and so we go from being full-sized humans who are the same size as the tree to being figures the size of the toys under the tree. I'm getting goosebumps just thinking about it. It's so cool. Well, if you're the stage director for that, you want the curtain to come up in exactly the amount of time that is planned so that everybody knows, you know, when this light bulb is here, I have to be there so they know their marks. I mean, it's, you know, some serious work. So we've got three motors to choose from. We have a 1 kilowatt, a 3.5 kilowatt, and a 5.5 kilowatt motor. Well, what does it take to get the curtain 7.5 meters? It's 193 kilograms. Okay, so we know that power is equal to work times time. Work is equal to force times distance over time. And we know the force needed to raise that curtain at constant speed is going to be equal to gravity. We're not accelerating it. We're just bringing it up at a nice, smooth, constant speed. So power is going to be equal to mass, gravity, the distance we need to take it, and the time we need to take it in. Well, let's see. I'm going to shrink that. Therefore, power equals 193 kilograms times 9.81 meters per second squared times 7.5 meters, the whole lot over 5.0 seconds. Let's get a run. Okay, so we get 2,839.99, etc. Gives us 2.8 kilowatts if we divide by 1,000. So we get a 2.8 kilowatt motor. We'll get it there in 5 seconds. The closest motor we have is the 3.5. So how long is it going to... Now, this is not part of the problem that's written in the book, but this is the kind of thing I'm always curious about. So if I'm setting this up, and these are the only motors I have to choose from right now. Well, the 3.5 is my closest. What's the time difference going to be there? I would like to know that, because if it's significant enough and I really need the 5 seconds, I'm going to go find another motor. So let's see what the time difference is between the 3.5 kilowatt motor and what would be our ideal motor would be a 2.8. So let's see. Power equals mass, gravity, distance over time. In this case, what I want to solve for is time. So delta T equals mass, gravity, distance over power with my 3.5. So delta T equals 193 times 9.81 times 7.5. And I got really sloppy, obviously. And the power available in my motor is 3,500 watts. Okay, so that 3.5 kilowatt motor is going to get it there in 4.1 seconds. You know, if I had a 3 kilowatt motor available to me, I'd probably go for that. It's going to get me closer to my 5 seconds, but that's what they want. That's what they want. Okay, assigned are, and these are in your PDF on page 81, number 1 and 2, so number 1 and 2 only. These are the 5F, page 181 in the PDF. Okay, I'll give you the rest of the time to work, and we'll mix FIP on Monday.